In this video, I want to discuss two important examples of integrals that we can do using integration by parts. I've written the first one here already, the integral of the natural log of x dx. So we've said that integration by parts works well when you can find one function, u, that gets simpler when you differentiate, and then you have another function, everything left over, that you can set equal to dv, and it doesn't get much worse when you take an antiderivative. So here, we know that ln of x gets simpler when we differentiate. We get 1 over x dx. And then what's dv? Well, it should be everything left over in the integral. So we just have dx. And when we take the simplest antiderivative we can, we just get x. So that means that this integral is equal to uv x times natural log of x minus the integral of v du. Integral of x times 1 over x dx. And this cancels nicely. We get x ln of x minus the integral of dx. So in the end, we get x natural log of x minus x plus c. So we can check that this works, that when we apply the product rule to this function, x natural log of x minus x plus c, when we take the derivative, what do we get? Well, we get x times 1 over x. We get the x times the derivative of the second part, plus derivative of x times natural log of x, minus the derivative of x, which is 1, plus 0, the derivative of c. And this is plus 1, and this is minus 1. So we just get natural log of x. So this example and variations of it come up all the time. So for example, you could try to do something like the integral of natural log of 5x. Let's do the second big example of an integral that we can do with integration by parts that we couldn't do before. Let's look at the integral of arctan of x dx. So arctan is a function where we know the derivative is 1 over x squared plus 1 dx. So that's a little bit simpler than a complicated function like arctan. So let's try just setting u equal to arctan of x. Then du is 1 over x squared plus 1 dx. And what should dv be? It should be everything else left over in the integral. So it should just be dx. And then v should be x, the simplest antiderivative we can come up with. And integration by parts says that this integral is equal to uv, which is x arctan of x, minus the integral of v du, which is x over x squared plus 1 dx. So how do we do this second integral? Well, the denominator, x squared plus 1, is kind of complicated. If that were equal to u, what would du be? It's almost what we have in the numerator. So the idea for the rest of this problem is now we do a U substitution, where u equals x squared plus 1. So du is 2x dx, or thinking of it slightly differently, 1/2 du equals x dx. So what this means, let me just rewrite this, is we get x times arctan of x minus 1/2 the integral of 1 over u du. So we get x arctan of x minus 1/2 natural log of absolute value x squared plus, absolute value of u. Let me do this in steps. Plus c, And we started with an integral involving x. We want an antiderivative in terms of x. So the very last thing we have to do is substitute back to get a function of x instead of this function involving u. So we can do that here, and we get x arctan of x minus 1/2 natural log of x squared plus 1 plus c. So there's one thing here. Notice I wrote natural log of x squared plus 1 instead of natural log absolute value of x squared plus 1. Why is that okay? Because the function x squared plus 1 is always positive. The absolute value doesn't change anything. So if you put an absolute value here, that's totally fine. I'm just saying that you don't have to. Last thing, you can check that if you take the derivative of this function, applying the product rule here, you'll get like an x times 1 over x squared plus 1. Taking a derivative here, you'll get a 1 over x squared plus 1. Everything will cancel in such a way that you just get arctan of x. So these two examples are important examples to know because natural log of x and arctan and 1 over x squared plus 1 are functions that'll come up again and again throughout the rest of this course. I'll also point out that this idea of what happened in this problem is going to be really common for the rest of the course. We start with an integral, we apply one technique, integration by parts, and we get a new integral we have to do. And we're going to solve that new integral with a different technique, U substitution. So this is an integration by parts plus U substitution problem. So we'll see that quite a bit going forward.